Hello, Honors Physics. The topic for this week still involves capacitors, and it also involves circuits. So instead of looking just at capacitors kind of as their own thing, it's about what they do once you put them in a circuit with other stuff. This is the summary slide from last week, so I'm going to go very quickly through what this says. The main property for a capacitor is called capacitance. Just like for a resistor, it was resistance. The definition of capacitance is Q over V. So this is like a functional definition about how the device operates. It tells you how much charge is needed to get a certain amount of volts across the device. For a idealized capacitor called a parallel plate capacitor, this formula also applies. K is the dielectric constant of whatever we put between the plates. Epsilon naught is a universal constant. A and D are the measurements of a capacitor. So A is the plate area, and D is the distance between those plates. One of the functions of a capacitor is that it can temporarily store energy in a circuit, and that's related to the charge that accumulates on the plates, because if you have positive charge here and negative charge here, they're attracted to each other, and so holding them apart from each other involves some potential energy. And we had 3 different ways of calculating that potential energy. The one in terms of Q and V is the sort of fundamental one, because that talks about charge and electric potential volts. The other 2 involve C, the capacitance of the specific device, in different ways. And when I put this photo in last week, I didn't explain the difference in appearance between these and the giant metal plates that I was talking about. Most of these capacitors are cylindrical, and the way they build those is basically they have 2 big sheets of foil, which are like those parallel plates. They put some kind of a dielectric between them. It might even just be like paper or some kind of a paste or something. But then they roll it up into a cylinder to save space. Not all of them are cylindrical, obviously, but that's one of the common ways of making a capacitor. So it's still based on that original idea with the big flat plates, even if it doesn't look like it. All right, so let's talk about putting these things into circuits. With resistors, the properties we were talking about all the time were the voltage and the current and the resistance. And there's that formula V equals IR, which is basically the definition of resistance. So the definition of resistance involves V and I, and that's why we cared about them. Definition of capacitance involves V and Q. So we're going to care about Q a lot more than we care about I when we're dealing with capacitors. But I want to remind you that Q and I are related to each other. I, when we originally defined it way back when, was delta Q over delta T. It's the rate of flow of charge, or the rate of change of charge when it comes to a capacitor. So they're related to each other. The Q on a capacitor, the charge that it's got, is based on the historical record of the current flowing in or out of that capacitor. If a lot of current has flowed in, then you're going to have a lot of Q. If that current flows out, then Q is going to go down, and so on. So series and parallel combinations. In some ways, series and parallel combinations for capacitors are just like resistors. If you put things in series, no matter what kind of thing they are, those things will always have the same amount of current as each other. So if I have the same amount of current entering this capacitor as entering this capacitor, that means they have to end up with the same Q, because, like I said before, Q is based on the history of all of the current that has flowed in or out. If they always have the same current as each other, that means their Qs are going to match also. The voltages might be different, and that depends on the capacitance value. If they're identical to each other, then with the same Q, they'd have to have the same V also. But if they're not identical, they could have different Vs. So I labeled them V1, V2. Now, conversely, if you put things in parallel with each other, and again, you might remember this with resistors, but if you put things in parallel, they all have matching voltages. The currents could be different, but the voltages are all going to match. So I've labeled my parallel capacitors with just a single V here that applies to both, but I've named their charges differently, Q1, Q2. And that's because if they're not identical to each other, the amount of current that flows in the top branch and the amount that flows in the bottom branch are probably going to be different. And again, that's just like with the resistors or anything else that you put in parallel. The different branches typically get different amounts of current. So that means the history of the top capacitor and the history of the bottom capacitor are different, and so they'll probably have different Qs. So both of these rules are essentially the same as we had for resistors. If you just kind of like smush current and charge together into one kind of larger concept here, these rules are the same. The things in series will have the same current or charge, whichever, because they're directly related to each other. Things in parallel will have the same voltage. So that part should feel very familiar. However, this part works out to be a little bit different. If I want to know about the total capacitance when I put things in series or in parallel, the TLDR, as you can see at the bottom, is that the rules are the opposite from what they were with resistors. So I'm going to give you a short hand-wavy version of the explanation for that. There is a longer, rigorous way of doing it, which the book goes through if you want to see it. But it's not necessary for this course for you to see or follow the more detailed explanation. The hand-wavy version is that if I put capacitors in series like this, it's very similar to just changing the amount of space between the plates. When we put resistors in series, I made an argument that was kind of like just making a longer resistor. And when you make a resistor longer, the resistance goes up. But if you increase the space between the plates on a capacitor, that decreases the capacitance. And you can see that in this formula that we worked with last week. C equals K epsilon naught A over D. So if D increases, C goes down. Similarly, if I put capacitors in parallel with each other, you could imagine just kind of like connecting these two left plates to each other and make a big plate. Connect the two right plates together to make a big plate. So a parallel combination is analogous to changing the plate area. And if you increase the plate area, that increases capacitance. Whereas with a resistor, if you make the resistor wider, that's like having a wider hallway and the resistance goes down. But with a capacitor, it goes up. So the result of all of that is that the rules work out to be opposites. Parallel combinations increase the total. Series combinations will decrease the total. Okay. So the series parallel stuff is one of the two big ideas for this week. The other big idea is related to the way the charging and discharging processes actually occur They take a certain amount of time, which you would have seen if you looked at the simulation video last week. You would have seen that it takes like a short amount of time for the capacitor to completely fill up or to completely empty itself. Both of those processes, the charging and the discharging, they start out fast because the beginning of the process is easy, effectively, and they get slower and slower as you go because the process gets harder and harder. So, for example, if you think about charging a capacitor, that means you've got this device, you're sending more and more current into it, and that plate is getting more and more positively charged as you put more current in. But of course, the current, the conventional current, is also positively charged. So as this plate gets more and more positive, it's going to get harder and harder for a positive current to flow at it because there's going to be a repulsive force there. So the process slows down. It gets harder and harder. It asymptotes towards some maximum value. So I have this dashed line here indicating the maximum. Technically, or mathematically at least, it would take an infinite amount of time to actually reach that final value. In reality, it's going to get close enough for your purposes in a finite amount of time instead. You just have to know, like, how close do you want it to get, and then that tells you how much time you have to wait, effectively. But it can get very close, such that it's like practically, for practical purposes, it's full, even in a finite time. So if you're charging it up, the function looks something like this. If you are emptying it, it looks something like this. And again, in either case, it asymptotes towards the final value, either some positive number or 0. If you wait a very long time, it approaches 0. The functions involved, I have written here. You can see that they both involve a base E exponential function. They're basically just flipped from each other and then offset. So, like, this is e to the negative x, more or less. This is negative e to the negative x. So that flips it over, and then it's just shifted up. That's what the 1 there is for. So those functions, these graphs apply for either Q, the charge, or V, the voltage. The current function, however, always has the kind of like decay form, at least if you're looking at the magnitude of the current. The sign of the current just talks about which direction it's flowing. But if you're interested in the magnitude of the current, it always looks the same. And that's a little bit weird, but it's because current is related to the rate of change of the charge. So you can see that in the charging case, the rate of change for Q is big at the beginning, and it's small later on. That's what this shows. And in the discharging case, the same thing is true. The rate of change here is, although it's negative, it still has a big magnitude. And then the rate of change gets closer and closer to 0. Physically, what's going on, I kind of already got at it, but like, if you're charging the capacitor, the amount of current has to go to 0 because eventually you're going to reach your like maximum charge. You can't just send current in forever. The amount of current has to drop down to 0. And if you are discharging it, then again, the current is going to have to go to 0 once the capacitor is empty and it doesn't have any charge to give anymore. So I will always approach 0, even though the other two could approach a finite value instead. So in those formulas, you can see there's like a coefficient in front for all of them. And that coefficient is like a vertical scaling factor for the function. The horizontal scaling is handled by this RC that you see here. So it's negative T over RC. So that's the resistance times the capacitance. So resistance times capacitance apparently is the same thing as a time. Ohms times farads equals seconds, which is one of the weirder unit interactions in physics. But that quantity R times C represents a time. And it's kind of analogous to a half-life in some ways. It's a little bit more complicated because this is a base E function instead of a base 2 function. The name of this quantity is the time constant. So when it comes to half-life, after that amount of time has elapsed, that tells you that in your radioactive sample, 1 over 2 is left over of your sample. 1 over 2 of however much you started with. Similarly, after a time RC has elapsed, you are left with 1 over E of the process that's going to occur. So instead of having 1 over 2 of your atoms remaining, you have 1 over E of your change remaining. I know that that doesn't feel really intuitive. Half-life is a lot easier to think about because it's both half has decayed and half remains, whereas here it's that 1 over E remains and 1 minus 1 over E has happened. It's not tidy. So I'm going to give a few examples. I have an animation running that I'll show you also, but it's not crucial that you have like a strong intuition for the way the time constant works. You just need to know it represents like the speed. So a long time constant means it takes a long time. A short time constant means it takes a short time. And the details you can rely on the formulas for. So 1 over E is roughly 0.37 or 37%. So I've got a graph here with 1, 2, 3 time constants labeled. So after the first time constant, I have gone 63% of the way to whatever my max value is. So there's 37% left to do. During the next time constant, during the next interval, RC, I again go 63% of the way from where I am to the finish line. So 63% of the remainder will occur during that next RC, which means the total is like around 86%. And that sort of iterative process continues. Steps get smaller and smaller until after an infinite amount of time, you reach 100%. So let me play an animation for you of that. Need to move my bubble out of the way. This is the growth curve. I've set the time constant RC to be 1 just for simplicity. So you can see that as the animation plays and the little dot traces through the curve, it's moving very quickly at the beginning. That's because the rate of change is big at the beginning. And it gets slower and slower with its vertical motion, with the growth. The growth gets slower and slower as it approaches the maximum value that I set to be 10. I can put some lines in These are just measurements showing how much it increases during the first few time constants. So you can see the first one is really big. Again, that's like 68% of the total happens during the first time constant. And then during the next one, 68% of whatever is left occurs. And then 68% of whatever is left after that. And then 68% of whatever is left after that. So the steps get smaller and smaller as you go. That is the basic idea with any exponential function. My little camera controls are in the way. Go away. I want to show you the discharging function also. But it really, really wants my recording controls there. All right, this is the discharging version. It's basically just flipped over. During the first second, during that first time constant, I lose 68% of the charge that I had. 37% is left. And then during the next time constant, between 1 and 2, I again lose 68% of whatever I had left, and so on. So again, the steps get smaller and smaller. All right. I can also adjust the time constant. Again, I have it set currently to have a time constant of 1. So it takes 1 second for this percentage to change. But if I make the time constant longer, bump it up to 2, you can see that the whole process is now slower. It takes 2 seconds now to get to where I previously had only needed 1 second. So the bigger the time constant gets, the slower the whole process is going to be. Okay, back to the slides. So, as I said a minute ago, it's difficult to deal with all of this completely intuitively. The best that I can come up with really is this statement here in quotes. So like during each RC, the value, whichever variable you're looking at, charge, voltage, current, whatever, the value changes by 63% of whatever is left. I think I accidentally said 68 a couple times in the previous, I'm sorry, 63. Changes by 63% of whatever is left. So as an example, these are the same numbers that were in my Desmos animation. If the time constant is 1, we're going from 0 volts to 10 volts. After 1 second, the voltage is going to be 6.3 because you have done 63% of your remaining change. 63% of 0 to 10 is 6.3. At 2 seconds, during this next interval of 1 RC, I need to increase by 63% of whatever is left. So what's left is this 6.3 to 10. 63% of that is 2.3. So I have an increase of 2.3. That gets me to 8.6. And the next time constant, what's left is 8.6 to 10. So I take 63% of that. That's 0.9. So I increase by 0.9, that gets me to 9.5. And so on and so on and so on. So again, you can see the steps get smaller and smaller. But this is like really tedious. It's not easy to even put into words. In a lot of the cases, it's just going to be easier to do the math. I have this formula. I plug in 10 for Vmax, plug in 1 for RC, plug in 4 seconds for T, and I can just calculate it on my calculator. I don't need to do all of this, like, oh, how many time constants is that? What percent am I going to be left with? Just, it's okay to just use the math when the intuition isn't there. All right, so this is the summary slide for both weeks, I suppose. Capacitors put in parallel can have the same voltage. Capacitors put in series can have the same charge. This is our definition of capacitance. This is how it's related to the size of a capacitor. That's those energy formulas again. These are the addition rules. And again, the addition rules are the opposite of the resistor addition rules. The charging and discharging process both involve an exponential function with an asymptote. Those are the functions for them. If you see something with a 1 minus e, that's a growth. And if you see just the e, that's a decay. The current always decays because you can't send current for an infinite amount of time. It has to go to 0. But the other two can either grow or decay. And the meaning of that RC, the time constant, is that during each time constant, the quantity will change by 63% of whatever is left in the process. And that is it. I'm also going to post a short simulation video this week so you can see the operation of an RC circuit. And there's also a lab demo video that another teacher posted before everyone was locked out of their classrooms. So you can see an actual circuit instead of just diagrams and simulations. And that's all I've got for now.